Hello everyone. In the previous chapters, we found a particle with a meter size quickly falls toward a central star due to interaction with gas in a disk. It is necessary to consider a mechanism to form a large particle with kilometer size from small solid particles in such a short time scale. A particle with kilometer size is called a planetesimal. We study formation process of a planetesimal in these chapters. In the first section, we studied the sedimentation of particles. In the previous chapters, we consider only radial motion of particles. Here we study the vertical motion of a solid particle in a disk. The second topic is the coalescence growth of particles. While a particle moves in a disk, it collides with other particles and captures them to increase its mass. We study growth process of a particle in a disk. Third topic is gravitational instabilities. As a formation process, gravitational instability in a disk was proposed. I will explain it in this section. First section is sedimentation of particles. Two forces are acting on a solid particle in a disk. One of the forces is a centrifugal force, because the particle is making a rotational motions around the central stars. And the other force is a gravitational force. Then we can decompose the gravitational force from stars into the vertical directions and the horizontal directions. So this could be considered the sum of the horizontal component of the gravity and the vertical component of the gravities. Then horizontal component can be cancelled out. There is no corresponding force in the vertical direction of gravities. Because of this gravity in the vertical directions, a particle sinks toward the midplane of a disk. Then practice 1. Write the equation of motion of a particle in a disk and find the terminal velocity of a particle in the vertical directions of a disk when the drag force is expressed by the Epstein law. But at first, we'd like to draw the figures. Central star has a mass of the M sub star. This is the midplanes. The position of the particles is here. Mass of the particle is the lower case of the M. Then vertical directions from the midplane is expressed as G. Distance is expressed as R. Then distance between the star to the particle is expressed as square root R square plus G squares. Gravitational force from the central stars expressed G, mass of the stars, mass of the particles over R square plus G squares. We can write the equation of motion in a cylindrical coordinate. dv sub r dt minus v sub theta square over r equal minus g m sub stars over r square plus g squares. Then we need to find the projections in the direction of r. So it should be r over square root r square plus g squares. Minus drag force is acting on the particles. F sub d over m, v sub r over u. This is the first equation. And F sub d, we use the Epstein laws. So drag force is acting on these particles when the particle is sink to the midplanes. This Fd can be expressed 4 pi over 3 r sub p squares is the radius of a particle times the density of gas, sound speed, and the u is the relative velocity between the particles and the gas disk. And also that we can write the equation of motion in the theta directions. dv theta dt plus b sub r b sub theta over r equal minus f sub d over m. b sub theta minus b sub gas theta is the rotational velocity of the gas over u. This is equation 2. And the g directions, dv sub g dt equal gravitational force gm sub stars over r square plus g squares, and g over square root r square plus g squares minus f sub d over m v sub g over u. This is the equation 3. So we could write the equation of motions. So gas velocity in the radial directions, and the gas velocities in the theta directions, and the gas velocity in the z directions. This quantity is 0. The v sub k square root 1 minus eta and 0 for the z directions. The relative velocities can be calculated. V sub r square plus v sub theta minus v sub gus theta square plus v sub g squares. Okay, then we'd like to solve these equations. We have already done this type of the calculations in the previous chapters. So we consider that v sub r is a very small value. We use the w to express the very small values. And the v theta is the Keplerian velocity, small quantity of the w thetas. And the v sub z is the w sub z. So w r, w theta, w g. All of them much smaller than the Keplerian velocities. And then we'd like to consider terminal velocities. Time derivative becomes 0. So we use this assumption to change the basic equation of the equation 1, 2, 3. And then from the equation 1s, so we have done the very same. So 2 w thetas v sub k over r equal f sub d over m wr over u. If you ignore the very small quantities, then from this equation 2st Stokes number w theta equal wr. So Stokes number is given by the mu omega sub k over f sub d. And from the second equation, you can find st wr equal minus w theta plus 1 over 2 eta v sub k. So we have done the similar calculation for the r coordinate and the theta coordinate in the previous chapters. But the new equations comes from the equation 3s for the equation for the g directions. Wg equal minus mu over f sub d's gm sub stars over r square plus g squares power index 3 over 2 times g. This can be approximated minus mu over f sub d. This is gonna be the omega sub k square times g using the st's minus st omega sub k g. So we have an equation for the z coordinate. Then st, we have already find out st is a Stokes number is a small values 4.3 times 10 to minus 7. R equal 1 AUs 3 over 2. And the rho sub p, material density of the solid particle is 3 gram per cubic centimeters. Pickard density of the rock, R sub p over 1 micrometers. We start considering the very small solid particle. We can estimate the vertical velocity of the v sub z is equal to w sub z. And then we can use this third equation. It becomes minus st omega sub k g. You can change the minus st h omega sub k g over h. Then this part is correspond to the sound speed of the sea. The sound speed of the sea is expressed 9.9 times 10 to 4 centimeter per second, r over 1 AU minus 1 over 4. Then you can substitute this into this equation to find out terminal velocities of a solid particle in the vertical directions. Is very slow velocities, minus 4.3 times 10 to minus 2 centimeter per second, r over 1 AUs 5 over 4, rho sub p 3 gram per cubic centimeter, r sub p 1 micrometers, and g over h. If we consider the very small particles, actually the height of the particle is approximately the height of the scale height. Velocity of a solid particle in the vertical direction is a quite small values. Then also we could find the WR. We have already discovered it's minus st over 2st squares plus 1 eta v sub k. Then if you take a ratio of these two values, w sub r over w sub g equal 1 over 2st squares plus 1 eta r over g. So st is a very small values. This could be approximate eta r over g. When eta r over g is less than 1, g is larger than the eta r. So in this case, w sub g is larger than w sub r. So particles sinks toward the mid-plane of a disk before migrating. So from this calculation, this is the mid-plane of a disk. And the particles actually start falling when the particle has a height of the eta r. When crossing these lines, radial velocity becomes faster than the vertical velocities. W sub g is less than the W sub r. So particle is following the disk curves and then finally migrating to the stars. I explained the path of particles in a disk. The final topic is the diffusion by turbulence. So we expect the turbulence is responsible for the diffusion of the particles. Particle is try to sink toward the midplanes, but diffusion prevents such a sinking toward the midplanes. The vertical speed of a particle due to the turbulence can be calculated. W sub diff is a z divided g square over nu. Then you can estimate W diff is a nu over z. Is diffusing velocities upward from the midplanes. So this is W sub diff. Equilibrium height of a particle is calculated. The equating these two velocity of the W sub g equal to W sub diff. So this is equal to these two quantities. This you can estimate the g square root alpha over st times h, because the nu is expressed alpha ch. Okay, we can estimate the height of the dust-rich layers. And the equilibrium height of the particle is obtained in this equation. So if you consider the size of the particle is 1 micrometers, z is 151 times the scale height. If the distance to the particles is larger than the scale height, we expect gas drag becomes too weak to prevent the falling process of solid particles. Largest z we can accept is the scale height. So particles' scale height can be estimated by the minimum value of the scale height and the g values. Now, for example, if you consider the size of the particle is 1 meter, then g can be calculated by substituting r sub b is 1 meters. Then it becomes 0.151 scale height. G value is shorter than the scale height. The HD is the height of the dust-rich layer. It becomes 0.151 scale height. Okay, in these sections, I explained the path of the solid particles in a disk, considering the vertical motion of particles. This is the end of this section.